So, test 3 material begins with the respiratory system. The respiratory system works very closely in conjunction with the cardiovascular system in order to accomplish one of the most important life-sustaining processes, at least from an immediate perspective. Okay. Your blood, as we talked about for the Chapter 19 lecture, serves as the transportation mechanism for pretty much everything under the sun that needs to be distributed throughout our body. But as far as an immediate concern, minute to minute, second to second, the cardiovascular's delivery of oxygen and removal of carbon dioxide becomes of the utmost importance. Because if that job isn't maintained consistently, tissues begin to die and death results if you are deprived of oxygen for too long a period of time. Problem is, one cannot work without the other. There's no point in undergoing gas exchange if the blood isn't circulating in order to deliver those gases. Vice versa, there's no point in exchanging gases if the blood isn't flowing in order to deliver them. So both of these need to be working to accomplish the goal of the exchange of gases and the delivery of those gases throughout the body. Now, if we want to be specific, the respiratory system is responsible for the actual exchange of gases, while the transportation of those gases throughout the body is the job of the cardiovascular system. Anatomically, we can classify the respiratory components 2 ways. First, we can classify them structurally. Structurally, we can differentiate between the two, between the anatomical regions of the respiratory tract by classifying them as either part of your upper respiratory tract or lower respiratory tract. If we're part of your upper respiratory tract, then we are above the larynx. An important characteristic of the upper respiratory tract is, for the most part, both food and air can travel through those tubes. When we get to the larynx, the epiglottis in particular forms our trap door, which starts the beginning of the lower respiratory tract. At the point of the lower respiratory tract, only air moves. Okay, again, at the beginning of the lower respiratory tract, only air moves through that region. Structurally, we classify the organs of the respiratory system as either being part of the conducting portion or the respiratory portion. Well, as we saw above, the primary function of the respiratory system is gas exchange, so the respiratory portion would be those areas that are actually able to undergo gas exchange. Now, that includes primarily the alveoli, or alveolus singular, alveoli plural. But in addition to that, gas exchange can also occur within the alveolar ducts and respiratory bronchioles. Now, if we're not exchanging gases, our only function becomes the movement of those gases to and from the respiratory zone or respiratory portion. And those regions are referred to as the conducting portion. And again, that makes sense because we're simply conducting those gases to and from the respiratory portion. Now, we are going to focus primarily on the lungs and different characteristics of the lungs as we talk about the physiology of the respiratory system. But we have a few other organs and regions of the respiratory system that are important and we are going to want to discuss briefly. Now, the majority of the conducting zone is going to be all of your upper respiratory tract and the larger tubes of the lower respiratory tract. Again, the primary job of these tubes is to conduct the air to and from the respiratory portion, but they do have some additional functions. So if we start first with the nose, of course, is the initial organ of inhalation. Its job is to bring air in to our respiratory tract, but it does have some additional functions. The nose is also responsible for your sense of smell, obviously. In addition, embedded within your nose, this being a human nose, we have all these bony ridges. These bony ridges are called conchae. These bony ridges are covered in highly vascular epithelium, which help to moisten and warm incoming air and cool and dry out exhaling air. Now this adaptation is extremely important in animals that live in very cold or dry environments. Over here we see a polar bear, and here we see one of the bison-like creatures, mammals that live up in Alaska. You'll notice that their conchae are highly have a lot more surface area associated with them. The more surface area, the more tissue, the more tissue, the more vascular, the greater their ability to conserve heat and moisture as air passes across them. So the nose also serves a very important function to warming and moistening incoming air and cooling and drying out exhaled air. This helps us both conserve heat and conserve moisture. So the nose functions again in smell. It's the organ of initial inhalation, warms and moistens your air. All of the hairs and the associated mucus of the nose helps trap incoming debris. And finally, your nose also serves as a resonating chamber. If you've ever had a head cold, or if you've ever had a stuffy nose, you'll notice your voice tends to change pitch. And that's because your nose serves as a resonating chamber for speech. So if you plug your nose right now, or if I plug my nose right now, you'll hear a change in my voice, and that is because my nose can no longer serve as that resonating chamber. Boy, that was fun. So there we have your functions of the nose. Moving into the pharynx connects the nose to the larynx and trachea, so it continues our passageway for air. Its mucus covering does, to a lesser degree, moisten, but not as much, moisten the air coming in. Pharynx also houses our tonsils, which you learned in the lymphatic system are going to be part of our first line of defense, so that if something gets inhaled that shouldn't have, we've got our immune cells ready and waiting right there to start the attack if necessary. Moving into our larynx is of course our voice box. For the larynx, in addition to serving as our voice box, the epiglottis becomes a very important structure that ensures food does not enter the trachea. Food and water does not enter the trachea. And of course the vocal folds allow for speech and sound production. The trachea, along with the bronchi, carry the air into the respiratory zone, the final way into the respiratory zone. These guys are aligned with, as you recall from AMP1, pseudostratified ciliated columnar epithelium with goblet cells. So this epithelium is coated in mucus from those goblet cells, which serves to trap debris as you inhale, because again, the air is going to have debris floating in it. Hopefully we can trap the majority of that debris in this mucus, and then we use the cilia to beat that mucus towards your pharynx, so that we can then swallow it or cough it out. You can see the importance of the cilia and mucus associated with the trachea and bronchi if you've ever either been to a smoky club or you've ever been a smoker, because smoke will actually paralyze the cilia associated with pseudostratified ciliated columnar epithelium. So what happens throughout the day, since you're actively smoking, all of those cilia get paralyzed and the gunk just accumulates in your trachea and bronchi. When you go to sleep, however, you're not smoking, which means the cilia wake back up again, so to speak, and they begin to beat. And as they begin to beat, all that mucus with all of that debris that was trapped throughout your entire day begins to move up towards the pharynx, which is why when you wake up in the morning, you have the so-called smoker's cough, because you've now had to eliminate what would have taken you, or what you would have eliminated throughout the day. You now are eliminating all at once the next morning because you weren't allowing it to move out of your trachea during the day due to the smoking. Once we get into the actual respiratory site, we're in our lungs. The lungs are organized into first right and left lungs, then individual lobes. Those lobes are further broken down into lobules, those lobules into alveolar sacs, and finally your individual alveolus, plural being alveoli. The alveoli is the primary site of gas exchange, as I mentioned, but in addition to the alveoli, gas exchange can also occur across the alveolar ducts and respiratory bronchioles. Now, the organization of the lung corresponds to the branching of the bronchial tree. You'll notice coming off of the trachea, we have our first branch. This is referred to as your primary branch, primary bronchus. The primary bronchus corresponds to your right and left lung. From the primary bronchus, we continue and we branch into the secondary bronchus. The secondary bronchus, 1, 2, 3, corresponds to the lobes of your lungs. That means on the right side you would have 3 secondary bronchi to correspond to your 3 lobes in the right lung, and on the left side you would have 2 secondary bronchi to correspond to your 2 lobes on the left side. Now, the lobular differences between the right and left lung correspond with the size difference. You'll notice that the left lung is slightly smaller than the right lung. The reason for this would be the location of the heart. Although the heart is, for the most part, located within the center of the thoracic cavity, it does sit slightly off to the left, which causes the heart to take up a little bit more of the left lung space and leave a little bit of extra space for the right lung. This is what allows the right lung to be larger and causes the left lung to be smaller. Finally, as you see here, our secondary bronchi branch into the smaller tertiary bronchi. These tertiary bronchi are what feed your lobules. So that lung lobe lobule organization that we discussed on the previous slide is corresponding here to the primary, secondary, tertiary branching nature of the bronchial tree. The lungs themselves, like the heart, are surrounded and supported by your pleural membrane. Pleural membrane is a serous membrane that surrounds and supports the heart, and as is the case with all serous membranes, it has 2 layers. So we have the outer layer here, which is called your parietal pleura. Your parietal pleura would be in contact with the ribs, laterally or inferiorly the diaphragm. Okay. Then lying on top of the lungs we have the visceral pleura. And in between the two we have our pleural cavity. Now this pleural cavity is filled with a small amount of pleural fluid that has a very high surface tension. This pleural fluid serves 2 very important functions. Not only does it act as a lubricating fluid to allow these 2 layers to slide past one another, the high surface tension creates adhesive and cohesive forces, which cause, for all intents and purposes, the parietal pleura to stick to the visceral pleura. Now, when I say stick, I don't mean that they're glued together, because even though they're adhered to one another, they don't necessarily, they're not glued together, because the layers can still slide past one another, but if you try to pull them apart, they wouldn't separate. So you can slide them around, but you cannot separate them. If you've ever put away 2 bowls that are about the same size, but they're not quite dry, when you try to pull them apart, the water causes them to stick together, but you can still slide them. You can still circle them, but they're not going to separate. So that's kind of what's happening here. Now this adhesive cohesive force that causes the parietal pleura to stick together becomes extremely important a little later on when we talk about the actual mechanics of inhalation and exhalation. So it's important to remember this characteristic as it will come up a little later. As we go a little further into the lungs, we enter up with the alveolar sac, and which is clusters of alveoli. So within a lobe, we have multiple lobules, and each lobule is made up of multiple alveolar sacs. These alveolar sacs are then fed by alveolar ducts and eventually branching into your individual alveoli. The alveoli is the primary site of gas exchange. If we take a closer look at the alveoli, singular, alveolus, this is what we see. In general, it is simply a gas-filled cavity, as we see here. So all of this is filled with air. Okay. Now the goal here is for gas exchange to occur across the respiratory membrane. This right here is your respiratory membrane. Now the respiratory membrane is going to be made up of your alveolar epithelium, a basement membrane, then a couple of basement membranes I should say, and then your capillary endothelium. So what we see is both the alveolar epithelium and capillary epithelium are a type of simple squamous epithelium with a very thin basement membrane between. What this means is the distance between the alveolus and the blood is extremely thin. This becomes important since the process of gas exchange is going to occur via diffusion, and diffusion occurs most effectively over very short distances. Now, this alveolar epithelium that's lining the alveolus is referred to as your type 1 alveolar epithelium. This type 1 alveolar epithelium serves as the actual squamous cells that line the alveolus, forming the diffusible membrane for gas exchange. But as the name implies, if there's a type 1 alveolar epithelium, there is probably a type 2 alveolar epithelium. Now, every so often, the squamous cells modify to form a type 2 alveolar cells. That's what this guy is here. And the job of the type 2 alveolar cells is to secrete surfactant. Okay? Surfactant covers the surface of the type 1 cells, forming a thin liquid coating. As we see here, it's called alveolar fluid with surfactant. This thin liquid coating covering the surface of the alveolus offers a couple of important functions. First, it allows the gases that are bouncing around up inside here to first diffuse into that alveolar fluid, making it much easier then for those gases to diffuse between the blood and the alveolus. Second thing it does is surfactant is a lipoprotein. Okay, now being that it's part protein, that means surfactant is going to be a polar molecule. Now, as you recall, polar molecules have a partial positive and a partial negative charge. And if we draw out an alveolus, as we see here, let's go ahead and coat it with some surfactant molecules. These surfactant molecules, because of their slight polarity, are going to be attracted to one another. The positive side of one molecule is attracted to the negative side of the other. Probably should have drawn this a little bigger. But you get the point. So positive, negative, positive, negative, positive, negative, positive, negative. So basically what ends up happening, if we have our big surfactant molecule, it's got a positive side and a negative side. That's what makes it polar, right? Well, that positive side is going to line up next to the negative side of its neighbor. And so on and so forth. Okay. Now, when this alveolus expands during inhalation, as we see here. Oh, let's make that a little bigger. As we see here, all of those individual surfactant molecules are going to get separated from one another. They're going to get pulled apart to a certain degree. Well, being that they're polar, do you think they like being pulled apart? Hopefully you're thinking, no, they don't. Which means when I stop inhaling, these guys are going to want to get back together again. That reattraction due to that polarity is what helps with exhalation. Okay. Now this is a good thing if this guy is only attracted to that guy, and this guy is only attracted to that guy, and this guy is only attracted to that guy. So a little bit of polarity is good. Too much polarity though can be bad, since it's not a good thing if this guy gets attracted to that guy over there, or if this guy gets attracted to that guy over there, or that guy over there, or that guy over there. What will happen if we have too much polarity is the entire alveolus will collapse. So what we're seeing here is that a little bit of polarity is good, too much polarity is bad. Well, that's where the lipo part of this molecule comes into play. I said it was a lipoprotein, and as you guys know, proteins are polar, but lipids are non-polar. So what we end up seeing here is that we make the molecule part protein to give it a little bit of polarity to help with exhalation and lung recoil, but we add some lipid components to make sure that that polarity isn't so strong that the alveolus collapses upon exhalation. So here we have some questions. Take a little break, see how we're doing. So pause if necessary as you read through this to see what you come up with. So which of the following statements is not correct? The lungs are located in the mediastinum. The right lung is larger than the left lung. The visceral pleura covers the lungs. The parietal pleura lines the thoracic cavity. And the parietal and visceral pleura are separated by the pleural cavity. Well, of these, the only one that is not correct is A. The lungs are not located in the mediastinum. Remember, the mediastinum or mediastinum is the central core of the thoracic cavity, housing the lungs and trachea, esophagus, etc. The lungs are located laterally to the mediastinum. The rest of these statements are true statements. Here's our next question. Notice double asterisks here, so that means there are multiple correct answers. So you want to choose all that apply. So pause if necessary, but if you think you've got your right answer, let's go ahead and see what we got. What is the function of the pleural fluid within the pleural cavity? Aids in recoil of the alveoli, acts as a lubricant to the pleural membranes, creates an adhesive cohesive force which causes the pleural membranes to adhere to one another, or it cushions the heart. Well, of all of these, B and C are correct. The reason why I put this in there is your pleural fluid is often confused with surfactant, particularly since they both have surface tension, they both have polarity characteristics that are essential to their functionality, but those polarity characteristics are different depending on, or not the characteristics are different, but the uses for that of that polarity is different depending on whether we're talking about surfactant or pleural fluid. So we already went through this one, but what is the function of surfactant? Here we see again two potential answers. See if you can come up with the other answer, since I gave you one of them on the previous slide. Okay, hopefully you figured it out. If not, go ahead and pause your recording while you think a little more. What is the function of surfactant? Well, we already saw from the previous slide that it aids in the recoil of the alveoli. But which of these other ones does it do, since we do see the two asterisks here? Does it create or act as a liquid medium for gas exchange? Does it create an adhesive or cohesive force which causes the pleural membranes to adhere to one another, or does it keep the alveoli collapsed? Well, of all of these, the only thing the surfactant is responsible for is going to be aiding in alveolar recoil and exhalation, and then creating the liquid medium for gas exchange. Bringing us to the blood supply of the lungs, a lot of people think or associate the blood supply of the lungs as being with your pulmonary arteries, which are carrying deoxygenated blood to the lungs in order to be reoxygenated. Problem is, that would mean the lungs are only receiving deoxygenated blood. But there's a lot of tissue associated with the lungs, much of which is not associated with gas exchange. And doesn't that tissue need oxygen? Don't the pleural membranes need oxygen? Don't the bronchi need oxygen? Don't the bronchioles need oxygen? Well, what we see is we're going to have a small supply of oxygenated arterial blood being brought to the lungs in order to supply the tissues not associated with gas exchange with oxygen and nutrients. So what we see is that is the job of the bronchioles. Branching off of your thoracic aorta, you have several small arteries referred to as bronchioles, which is going to carry oxygenated blood to the regions of the lungs which don't have access to that oxygen being used for gas exchange. Of course, this supply to the lungs via the bronchioles is much smaller than the supply coming from the pulmonary arteries. Pulmonary arteries are, of course, bringing deoxygenated blood to the lungs to get reoxygenated. Although we may have two separate supplies for blood to the lungs, we have one common exit. Okay, all blood, whether it's coming from the bronchioles or whether it's coming from the pulmonary arteries, is drained via the pulmonary veins. So technically, the blood draining into the left atrium from the pulmonary veins is technically 99% oxygenated, 1% deoxygenated, approximately, since it is mixing with a little bit of the deoxygenated blood from the bronchioles. So we're going to go ahead and stop here, and we'll come back with the next section, which talks about the mechanics of inhalation and exhalation.